How's everyone doing?
Good.
Alright. Give me just a second to collect my thoughts. It's Friday. I am sleepy. We have a weekend ahead of us, but also a test next week, so do keep that in the back of your minds. How y'all feeling? I think I asked that already. Questions before we get started? Actually, I'm a little scatterbrained today, so forgive me. It might take me a second to actually get on track. Apologize. I apologize for that. Okay, today is Friday, March 4th. This is the weekend before our first test. That test will be given next week during lab time. There won't be a lab, instead you will take your test during that time block. So be studying over the weekend. As a reminder, there is practice questions and a list of topics for you to peruse. And one of the things I want to do today is open the floor up to any questions you guys have about that. Additionally, you have a lab due today. It is okay if you take the rest, like if you take it today to finish it up. The last question especially is kind of a small research thing. If you haven't started that one yet, it's like you Google a term and then you describe the term, but you know, it is something you have to spend a minute doing. So if you need to, I will take the labs today, but you can email it to me or you can slide it under my door when you're done. Either or works. But if you have it now and it's finished, I will take it at the front of the room whenever you are done with it and ready to turn it in. There is also the Chapter 4 homework and quiz, which are due midnight on Monday. I do encourage you to try to have those finished over the weekend, and I encourage you to use finishing them up as study time for the upcoming test. The sooner you finish it, the sooner you will know how you did on it, and also the sooner you can prioritize just reviewing for the test as a whole, because the test is more than just Chapter 4. What I want to do in class today is maybe just talk about a couple more things from Chapter 4. I introduced the idea a moment of inertia, but I haven't necessarily shown you it in any math yet, so we will do that in a moment. I also want to open the floor up to you guys for any homework or test studying related questions that you guys have. And hopefully we can all move on to a nice weekend after that. So, questions, inquiries, needs, etc. at this time. Yes?
So on the lab, question number 3, part B, it's talking about a force being applied to the end of an object. The formula is torque equals radius times force.
3B?
Yeah. Did I do that wrong?
Oh, I'm looking at the wrong document. No, that one's on me. My mistake. I had the wrong file loaded. All right, 3B. So, we have in my head I was envisioning this as either a wrench or just a pipe. So, something that is, I think I said 90 centimeters long.
That was kind of the question, is that I wasn't sure if the radius was meant to be radius or a diameter based on that number.
Yes. So, what the question says is, this piece of debris is floating through space. Since it's floating in space, we can assume no force, all the forces on it add up to 0. It is not accelerating, it's just drifting constantly. And some force is going to be applied at its end, one of the ends, it doesn't really matter which. And you are told that when this happens, the object is going to begin rotating about its center of mass. Most objects do this if I can't really replicate taking something in space, but in general, if any object is not specifically forced to orbit about some end point, it will usually rotate about its center of mass. So if this pipe was free drifting and I pressed just on one of its sides, it would try to rotate about this point, which means that the radius of rotation would be half of its length, not its full length.
Okay, so it is the idea of it being radius instead of diameter from that.
Yes.
Okay.
As it relates to our formulas, radius in formulas that we use in this class, it does refer to half of a circle, but sometimes the circle could be formed by one object rotating about one of its ends, and then its length would be the radius of such a circle. Or alternatively, in this case, the circle is formed by the object rotating about its center, so half of its length would be that radius. So sometimes it helps to draw the actual circle that will appear because of this. So what this question describes, what 2b describes, is this situation here. It's going to spin about its center, and so this half of its length is the radius of that circle. If it was rotating about one of its ends points instead, then its whole length would be the radius. It just depends on how it's rotating. Does that help?
I'm still a bit confused how you know exactly. So it's like the difference between it like rotating versus it. I'm sorry, I'm confused.
It's okay. I will try to make it clear within my wording exactly what is happening to an object. I'll also try to provide pictures where applicable. Sometimes it just comes down to what the question says. And I didn't provide a picture for this one. I apologize for that. For part 3, we have the description of the object. We have its mass, we have its length, we have the force acting on it, and we are told if the force is applied at one of the ends of the object, and my grammar is off, if its axis of rotation is its center, what will the torque on the object be? And that is meant to be the clue as to how to draw the picture, meant to tell you which of those two circles will actually occur here.
So the key phrase is that it was hit on one end of the object instead of just saying, hey, the whole thing was hit?
Yes.
Okay.
Usually if you just want to push something forwards, you kind of want to push on its center of mass. Well, a good example is actually this tire. If I want to make the tire move forwards, I'm better off grabbing it by its axle, its center of mass, to push it, than I am grabbing one of its spokes. Because since this force is a distance away from its center of mass, that can induce some rotation, even if I'm not trying to induce rotation.
Okay.
So, minor tip that might be useful to you. If you want to push something forwards, try to push on its center of mass, where most of its mass is located. In the case of human beings, that tends to be right about here. Any other questions relating to this lab? I guess actually, while I have the document up, there is something else about this I would like to talk about. I'm going to scroll down to question number 5. This question is designed as kind of a tiny little independent research assignment. Given the situation, I just want you to look up a few key terms and describe them to me. The key term here is angular momentum. Now, this is something that we're not really going to be doing math for, so the point of this question was just so that you could research it on your own time and have the concept in your mind. And it is a useful concept, we're just not going to be doing any math for it. the video that it links you to is a situation I've mentioned before. Oh, it's loading on the screen. And it refers to the idea that a bicycle, oh come on. A bicycle, when launched forwards without a rider, can remain upright and keep rolling forwards, again with no human intervention. Eventually something will knock it down. It'll run out of energy or something will push it, it might hit a rock. But it can remain upright and moving forwards on its own for a length of time. Your goal for question 5 is to, looking up the definition of angular momentum, explain why that happens. And I actually want to instead demonstrate to you guys. I have here a bike wheel, and when I spin it, I exert a force on the side, I exert torque to angularly accelerate it, now it has angular velocity. And we know from the linear world, when objects with linear velocity and mass are moving, then they must have some amount of momentum telling them keep moving forwards in that same direction. The same is actually true of rotation. When objects are spinning, they have angular momentum telling them to keep spinning in the same way that they are currently spinning. If you have forwards linear momentum, then you're compelled to keep moving forwards. If you have, say, clockwise angular momentum, the object wants to keep rotating clockwise. But it can get a little weirder than that, actually, because in the case of a rolling tire, if it's rolling a specific way, like say it's oriented up and down and it's pointing in a certain direction, it wants to remain oriented that way because of its angular momentum. It doesn't want to change at all. And so attempting to change the rotation of a spinning object can create some weird results sometimes. Could I actually get a volunteer to hold this? I'm going to ask a student to hold the tire like this, and I'm going to spin it while it's in your hands, and then I'm going to ask what you feel as you try to move the tire. Anyone willing? All right, thank you very much. So this is a normal bike tire. It came off of a bicycle. You just hold the two handles there. Yep, perfect. Now I'm going to spin it up, and once it's in motion, I'm going to ask you to try to tilt it back and forth. I just want you to report to the class what that feels like. All right? So just for starters, baseline, holding it still while it's just rotating, how does that feel? Just holding an object. All right, so nothing weird yet. Now try tilting it.
I don't know what I'm doing.
Would you at least describe it as weird?
Yeah.
Okay, we have confirmation of weird. Thank you very much. So, the tire's angular momentum means that it wants to keep rotating exactly the same way. It doesn't want to tilt. So it's literally fighting you, exerting a force on your hands as you try to tilt it. And this is one reason why learning how to ride a bike is so hard. Yes?
So, when I was little, my dad was trying to teach me how to ride a bike, and he kept on telling me you have to go fast enough. Is that part of the reason it's difficult? Because you have to go fast enough that the bike balances itself, basically?
It helps, yes, because remembering the formula for linear momentum, mass times velocity, the faster you go, the more momentum you have. The same is true here. The faster something spins, the more angular momentum it has, and the more it wants.
Upright.
Yeah, the more it wants to stay upright. So yes,
Okay.
the faster the bike, the more likely it is to stay up, as long as you don't turn the handlebars or adjust your center of mass too much.
So you just have to keep the handlebars steady, not lean over, and you'll actually stay up.
Ideally, yes.
Uh,
Just don't, hit any rocks, or in my case, a mailbox. What can also be kind of interesting is, you don't even have to be holding it for this to be true. Let's see. How do I do this by myself? Okay. If the wheel is just not spinning, and I let it hang from this rope, it will just drop. It actually gets some help. It's hard for me to do this with only 2 arms. Thank you very much, sorry. All right, if you could just hold it like you were before. I'm going to spin it up again, and then I'm going to hold it by the rope, and I'm just going to ask you to let go. All right, so spinning. I am only going to support it by the rope. Let go. It's trying real hard to stay upright. It is fighting gravity. This is a gyroscope. Those toys that remain upright as long as they're spinning, or at least try to.
or like a top, like a dreidel, yeah.
Yep, tops, dreidels, that's all angular momentum trying to keep the object upright. And if you can try this out yourself if you want to at the end of class. Doing this feels real weird because it's fighting every single turn I make right now. I swear, the twitching is the wheel acting on my arm. So, concepts related to angular momentum. A surprisingly useful thing, or at least it comes up surprisingly often, I find. Any other questions related to the lab assignment? All right. I am now going to refer back to our Chapter 4 notes, because I want to make sure to talk about moment of inertia with you real quick before, well, definitely before the homework is due. Because I named this, but we didn't do any math about it yet. I have referred to moment of inertia as the angular counterpart to mass. And we've seen this formula. I have shown it to you primarily in the angular torque formula that is the counterpart to Newton's second law. We compared last time force equals mass times acceleration to torque equals moment of inertia times angular acceleration. These two formulas define force and torque respectively. Linear forces cause linear accelerations on objects with mass, and torques create angular acceleration on objects with mass. Now, I have studied physics for my entire adult life, and I guarantee you that if I could just write M here, I would love that fact. I would love if, I hate that mass has an angular counterpart, because it just makes life harder. Moment of inertia has the potential to be a big pain. The reason why is an object's mass by itself is not the only determination of how something will rotate. For example, I really should never put this thing down because I keep referring back to it. This bike tire has roughly the same mass as this piece of metal in my hand right now. And yet, they're very different shapes. Their masses are spread out across different areas, they have different radii, and they will spin in very different ways, all because of their shape and mass orientation. Just their masses being the same doesn't create the same rotation in them. If having the same mass did guarantee the same rotation, then if we exerted the same torque on both objects, it would create the same angular acceleration. But it doesn't. The reason why is where an object's mass is affects how it's going to rotate. And not just that, but also what axis you are trying to rotate that object about. This wheel, all wheels, are very specifically designed to rotate like this. But I could rotate this in different ways. If I wanted to, I could try to spin it like this. Is this nearly as effective at accomplishing the wheel's goal? No. Hypothetically, you could build some type of weird strafing tank that uses wheels like this, but it wouldn't be the most efficient in terms of the forces involved. You could also spin it like this, but this definitely won't roll, not easily. And I guarantee you, these last two methods are taking more out of me than just rolling it across the ground. It takes more energy for me to do this than to do this. Because the way an object rotates affects how easy it is to make it rotate. Wheels, this is super easy because of the way it is spinning, because of the axis it's spinning through, and because of where the wheel's mass is. Ow. For an extra demonstration, this is my calculator lid. And I'm using this because I'm going to throw it into the air, and I don't want my whole calculator to hit the floor. This object, what I'm going to demonstrate to you now is a different object rotating in different ways to show why the axis and the orientation of the object's mass is important. So we're going to treat this as just a rectangle. Let's just assume it's a solid rectangle and that it's uniform all the way through. It's not, but we'll assume that for simplicity's sake. So it would be the same as if you were just throwing an eraser or a box into the air. And what I'm going to do is I'm going to throw this into the air in 3 different ways, spinning it through 3 different axes. First, I'm going to throw it into the air like this. Then I'm going to throw it into the air like this. And lastly, I'm going to throw it into the air like this. And it's the same object every single time, and I'm going to be applying roughly the same amount of force every single time because it's my same arm doing one repetitive task. And I want you to observe the different spins that result from that just based on which axis it's spinning through. So first, I call this the easiest one. I'm not very coordinated. But I want you to notice how it spins, how easy it spins, and how quickly it's spinning. No complications, nice and stable. Anything out of the ordinary? All right. Now I'm going to do it like this. Any observations?
More rotations that way?
It is spinning more times, you are correct. It's rotating more often. Even though I'm using roughly the same amount of force, it's spinning faster about this axis. And that's because, technically, spinning this way, its radius is smaller than when I spin it this way. I can't really show it very easily. But this is a bigger circle than this is. The radius is different, so that causes a slightly different rotation, even though it's the same object with the same amount of mass. Now for the last one. Now I'm going to do it like this. And this is probably the way most people absentmindedly flip their phones into the air. So I want you to pay attention to see if you notice anything weird. Besides the fact that I dropped it. Okay. Notice anything very different from the previous two? Does it just rotate straight the same way the entire time?
No.
No. It does kind of a weird backflip in midair. And I don't necessarily encourage you to try this with your phones. I'd say try it with a dumb object like the calculator lid. But throw this in the air enough times and you, if you're more coordinated than I am, every time you catch it, it might end up upside down, even though it should only rotate and land. Excuse me, I think I was mixing my metaphors. Can you notice the backflip? Can you see it kind of turn over in midair a few times? And you've probably seen that if it's the same thing with phones, because this is basically the same shape. I'd try it with mine, but it's the camera right now. Rectangles just do this if you rotate them specifically about this axis through the short end. And it's entirely because doing it this way creates a very weird moment of inertia based on its radius, based on its mass orientation, that just compels it to flip in midair. No other shape does that, to my knowledge. It's just a weird quirk of this specific shape. The shape matters, the mass itself does matter, the axis through which it rotates matters, which means every single object spun every single different way has a slightly different moment of inertia. Now what that means for this class is that usually in questions you'll be given everything you need to find moment of inertia if it ever comes up. Say, in a question I tell you this much torque is acting on an object and it angularly accelerates at X rate. Use that information in this formula to solve for the moment of inertia. That could be one of the questions that I ask. You would have everything you need to use this formula to solve it without having to look up what the moment of inertia of such a shaped object would be. But just to give you a brief glimpse at why this concept can be a pain. These are 6 different objects and different rotation configurations. And all of them have a slightly different formula for determining their moment of inertia, just based on what shape they are and how they are spinning. If you have 2 cylinders, same mass, same radius, but one of them's hollow, you have a different formula for finding their moments of inertia. If you have the same rod and you just rotate it about 2 different axes, that changes its formula for moments of inertia. There's infinitely many ways that many different calculations for this particular concept, and that's why you will have to memorize none of them. If you need any of these formulas, I will give them to you in a question. I will make sure this table is available to you. More realistically, I will give you torque and angular acceleration, and you can find moment of inertia using this formula. The main things to remember is moment of inertia represents how easy it is to spin an object in a specific way. The lower moment of inertia is, the easier it is for that object to spin in that particular fashion. Thinking again to the wheel was designed to spin like this. If something is easy to spin in a certain way, it must have a low moment of inertia. Whereas if you try to do it the wrong way, it would have a higher moment of inertia because it's just harder to spin it like this. It takes more torque on my part to get it to move. So, moment of inertia is just a numerical representation for how easy it is for an object to spin in a certain way. I would like to get one example that uses that fact in your notes very quickly. We started talking about torque with wrenches. Let's conclude this conversation with a different wrench. Let's say we have a wrench with a mass of 15 kilograms, and I have already calculated its moment of inertia for you. 1 kilogram times meters squared. It's a weird unit. I don't remember it half the time. It's not going to be very important. But for this particular case, we know for absolute certain I equals 1. So, mass, 15 kilograms. Moment of inertia, I is 1. And we are going to exert a force of 200 newtons upon this object. So, first question, if we exert that 200 Newton force on this 15 kilogram wrench, what will its linear acceleration be as a result of that?
One.
Not quite. So linear acceleration is good old-fashioned acceleration, just A. We know the force we're exerting on the object, we know its mass, we can figure out how much it will normally linearly accelerate as a result of that force acting on it. So this right now is the old stuff, the old method. We want to know if we just push on this wrench, how much will it accelerate because of that? We exert 200 newtons on an object with a mass of 15 kilograms.
13.33.
Thank you very much. So that's the old method. That's good old-fashioned linear acceleration. Next question, what will the wrench's angular acceleration be if we apply that force on its end and it starts spinning about the head of the wrench? So, oh no. I made a mistake. I apologize. I didn't mention how long the wrench was, which is a unique variable. My mistake. All right. So I've added one more known variable, that is the wrench's length, 50 centimeters. So, we have a wrench, we're going to be exerting a force on one end of the wrench. That end is 50 centimeters away from the side that will be doing the spinning. We're told, what will the wrench's angular acceleration be if it rotates about the other end when we push on this side perpendicularly? So we are applying a force some distance away from the fulcrum. We know that force, we know the length, and we know the object's moment of inertia. we were told that number, we don't have to look it up. Thoughts on possible steps? All right, we have enough information to figure out the torque on this particular object. We looked at two formulas for torque. I'm going to list them both. We have perpendicular radius times force. We also have moment of inertia times angular acceleration. So, we actually know the radius of rotation. In this case, it's going to be the whole length of the wrench because we're applying the force here, it spins about this point, and so that means the length of the wrench is the radius of the circle we're going to create. We know the force, so that's good, which means we have everything we need to find an actual number for torque. Looking at the other formula, we're able to find something, a number for torque, and we know moment of inertia because the question just told us. And the last thing is angular acceleration, which is what we want. So my recommended solution here is to combine these two formulas. They're both equal to torque, so I'm just going to set the two equal to one another. Radius times force equals moment of inertia times alpha. I just took the two things that were equal to torque and set them equal to one another. We know the radius, 50 centimeters, is half a meter. We know the force, we know the moment, and all that's left is alpha. And I think that would be 100 radians per second squared. Questions, comments, needs, concerns, etc. Okay. In my opinion, this is the weirdest part of rotation. And, yes, sorry. Absolutely, yes.
Number 8, it's got a pendulum angle. How do we solve that?
So that one, the picture that's drawn might make it seem a little trickier than it actually is. If I'm remembering which question that is correctly. I checked over it recently. The pendulum one, I think, was just an arc length question. Or at least I would solve it like an arc length question. Oh, that's quiz. Sorry, I wrote the wrong thing. Alright, so homework question 8, pendulum shown below, sweeps through a known angle, so we know the angle between here and here. And we know the length of the actual pendulum itself. And we are asked, how far does the pendulum bob travel in one complete cycle? Okay. So I will admit, it's not entirely immediately obvious what is being asked for. It wants to know this distance. It wants to know the the distance from here to here in meters. Now this arc is just one part of a much larger circle. So this pendulum is rotating. This is technically circular motion, which means that this piece here is basically just an arc length. So, what I would recommend is we know the angle, the change in angle from one position to the next, and we know the radius of the string, which is also, we know the length of the string, which would be the radius of the circle formed by this arc. And I recommend using the translation formula to convert between that angle, basically, and the corresponding arc length. In the notes, it might list this as S, because that's the geometric formula for arc length. I'm using delta D right now. So, we know angle, we know radius. We would be set to solve for this. The one small problem is this formula is designed for radians, not degrees. So we do need to convert degrees into radians first. If you'll recall, 2 pi rad equals 360 degrees. Which we can use to convert however many degrees your version has into radians. Mine is 43.1 degrees. 360 goes on the bottom. Degrees is a unit, so it does cancel out. And that will tell us the number of radians. Once you have that number of radians, you should be able to multiply it by radius and get your distance in centimeters. Make my work real quick. Oh, I see the problem. This question thinks it's tricky. Okay, I'm glad you asked because there was an element to this that I didn't expect. I apologize. Doing this, using my sample numbers, I got a number of radians equal to 0.75. If I plug that in for delta theta, with my string length of r equals 53.1 centimeters, and solve for delta d, I get 39.94 centimeters, which is all well and good, except that's not what Achieve is looking for. And I do know what happened here. The issue is official physicists consider one complete cycle of motion of a pendulum as being, because if you think of how a pendulum moves, one complete cycle is forwards and then, forwards and backwards. It's wanting the pendulum to go out and then come back. And that is what physics textbooks consider one full complete cycle. So it does this twice. I got 39.94. Multiply that by 2, and I get approximately 79.9. Because it does this arc twice, once as it goes forward, once as it goes back. That one's on me. I apologize. I didn't realize it was going to do that. Does that help? Okay. I'm sorry, I wasn't expecting that curveball in that question. I'm glad you asked, but I'm sorry for the number of steps I wasn't expecting there. Any last questions before we break for the weekend? Okay. Be studying for the test, and let me know if you have any questions on it, or as you finish up the homework over the weekend, and hope things go, hope you have a nice weekend, and I'll see you Monday.